So this is, in a way, a reprise because a couple of years ago, one of the first talks I ever gave to LCTG was about why we need quantum mechanics. And it's recorded. Steve did his usual good thing, and I think you can download it from Lex Media, and it's also on YouTube. So I thought maybe what I would do today is just put up one slide saying, here's the link, go look at the talk. It was just what it was before. But I couldn't actually bring myself to do that. So I'm going to talk about quantum mechanics, why we need it. And today I'm going to talk about how quantum mechanics resolves the kind of major conceptual difficulty, trying to distinguish in physics between particles and waves, between an object which is highly localized, has mass, very distinct mass, very distinct momentum, and an object which is much more distributed. You know, we think of waves of water as just ripples that cover the surface of the material. We are also interested in sound waves, which are disturbances that propagate through air. And then we're interested in light waves. And in fact, historically, there was a big question about whether what the nature of light is. Newton wasn't sure, but he came down on the side of particles. He said light is some kind of particles. And Newton, being the godhead of physics, ruled until the beginning of the 19th century, when Young showed that light waves undergo interference. And I'm going to talk a little bit about interference because in the end, the way you decide that something is a wave is whether or not it will exhibit interference. So interference becomes the kind of touchstone. If it will produce this phenomenon of interference, it's a wave. But before that, I'm going to, this is a little bit of a tough audience to deal with because most of you guys have had physics, sometimes a long time ago, but still, I mean, you know about wavelengths and you've been signal processing all of your lives. And but all right, be that as it may, I'm just going to go back and review some of the basic features of waves because I think I need to do that. And I'm going to talk about wavelength and frequency and velocity. And then what's really crucial, getting us closer to quantum mechanics, is the waves have this property that they will add together in a very straightforward way. We call that superposition. And I'm not going to talk about traveling pulses today. So here I want to talk about waves. How do you know if something is a wave? You know it's a wave if it exhibits interference. So I wanted to show you a wave, and I can do that very simply by just writing down a trig function of a cosine of x. Everybody see that all right? And there it is. And there's a nice cosine wave. And you see this would represent, if it were a sound wave, it might represent the decrease in density at a certain point in space and the increase in density. And so this would be a pure frequency tone being transmitted in a set of parallel pulses down your along a pipe or from your mouth to my ear. And you know that the distance from one point of similarity to the next, that's the wavelength. So this thing has a wavelength of 6 of these little squares. And the height is called the amplitude. And if I made this thing move, and I could, but I won't do it. Well, I can make it move like this. Here I am being clever, I think. I can make it, no, I know it. Never mind. If I make it move, then the time it takes for one point of amplitude to move this distance is called a period. And the reciprocal of that is the frequency. And, I'm not telling you anything. I think it's profoundly new. But I'll come back to this in a minute. So let's go back to my my properties. Does that work? Yes, that works very nicely for a chance. And so sort of the mysterious wave. I mean, we actually are probably accustomed to say water waves. That's so just to remind you of simplicity. Here's a little photo, and you can see somebody has thrown a pair of stones into the water. Nuts. They've thrown a pair of stones into the water, and ripples have spread out. And that's a familiar story. And so instead, we're going to mechanize it, and we're going, there you see the spreading out, and you can see the interlocking ripples make a pattern of maxima and minima. And you can do this in a ripple tank. And here's a very nice picture of a ripple tank. It's got a nice apparatus here with little plungers that bob up and down in the water and make the ripples, and the ripples spread out. And now you can see the pattern below. The ripple tank was invented at, of all places, MIT, back at the end of the 50s and the beginning of the 60s, when the Physical Sciences Study Committee was centered there, reforming high school. So you get this pattern of maxima and minima. And this is done on water waves, perfectly obvious, but you can also do it with light. And of course, that's what Young did. He had two optical slits, and here, like a slit here. And so now you imagine that this is a flat piece of cardboard, and we're looking down edgewise down the cardboard. And so there's a slit here, and there's another slit here, and the light comes through the two slits. And just like the water waves, it's combining so that when it hits a screen back here, there will be a minimum and a maximum and a minimum and a maximum and a minimum and a maximum. And here is an actual pattern of what you get when you put the light through the through two slits. And this is a little harder to see. If you look at it coarsely, you'll see there's a big bright blob here and a fainter blob there and a fainter blob there. But if you look closely, you'll see that the big blob is divided into small little islands of light with tiny black lines between it. Can you actually see this well enough to?
Yes.
Good. All right, good. So actually what's happening here is you're getting two different kinds of interference pattern. If you had only one slit, you would get the bigger blobs. You'd get this one and you'd get this one. But as soon as you put in the second slit, you get these subdivisions. And this is called an interference pattern. Why not? It's a pattern and it's produced by interference. And it is because Young was able to produce this and visibly see it, that beginning of the 19th century, people realized that light has to be a wave. It is not made of particles. And so that's kind of half the story. The other half of the story, of course, is that in a little while, we're going to find out that, well, light is particles. And that's where we're in trouble, but I'll save the trouble for a little bit further on. Now, let me show you just because I want to see if I can do this. This is, again, kind of playing with, let's see, let's go new share. Let's go advanced. Let's go content from second camera. And I think, and that share. Oh, yeah. So here I am under my external camera. I put my hand down there, there it is. The second, I was hoping at some point to use this so I could write down, complicated equations like E equals mc squared, but the latency is so bad. I've done it, I've said I've done it, and now it's slowly appearing on the screen. So that's not exactly wonderful. But what I wanted to show you was what happens when you have many slits. The diagram in the previous slide was showing you what you get when you have 2 slits. Well, I have here in my hand a nice object, which is a diffraction grating, and it has 500 slits per millimeter. So it has a lot of slits. It has so many slits that it actually looks transparent. And they're in fact little grooves in a piece of plastic. But the interference pattern that you get from such a thing is quite striking and rather useful. And I just thought I'd show it to you. And I'm going to show it to you using a laser, which, because no home should be without a laser. Here I have one in my hand, and you see if I turn it over, and I've turned it over. Now come on, picture, you turn it over. Very good. And you see, now I turn it on, and lo and behold, there is a spot. And the thing that's kind of neat about it is if I take my laser spot and I put it through my diffraction grating, you see now 3 spots. And in fact, if you have keen vision and look, you'll see a fainter spot up there kind of under the mc squared. Well, all right, that's not too great. But you see again, very much an interference phenomenon. All these slits together have the effect of producing multiple beams from the single beam. This is a basic tool for studying emission. Anybody here who has done spectroscopy knows that atoms will emit different wavelengths of light, and you can separate out those. You can actually separate out those different wavelengths of light using a diffraction grating. It's the same. It's doing the same sort of thing as a prism did in Newton's day when he first discovered that white light has a composition. So that was my demo. All right, and you can see doing a demo on Zoom with 4 pieces of apparatus is not very efficient, but I wanted to try it out. So I'm going to do a little digression here. So here, let me just sort of summarize where I think I am at in talking to you right now. We've talked about interference. I've tried to show you that light is a wave and that it has those properties of wavelength. In fact, I didn't show you everything I wanted to show you. So let me go back. I think. Here, yeah. So here I am back here, and we saw what wavelength is for that thing. The little curve that I drew on the graph had a wavelength of 6 units. Maybe those were sort of fractions of centimeters. Here is the visible spectrum spread out. And under here is an attempt to show you that you're going from longer wavelengths to shorter wavelengths as you go from red to blue, something which I think everybody here knows. What they don't tell you is that
I'm not seeing any of your chart. Are you showing a chart now?
I am, and it's showing up on mine just fine.
I see it.
Yeah.
John, yeah, move stuff out of the way. There's something in the way that you're not seeing it. That happens to me sometimes too.
Yeah.
I got it.
Okay, John?
Yep.
All right. So anyway, I'm just showing you the visible spectrum, red to blue. And then here, I think interesting is the wavelength. And we were looking at something that was centimeters on the screen before, but now it's saying that this wavelength is 635 nanometers in the red. Nanometers 10 to the minus 9th, a billionth of a meter. And you go from longer wavelengths through the yellow, the green, to the blue, to the ultraviolet. at 400 nanometers. And the frequency is, well, in fact, the product of this number and this number, the product of 635 and 480 will turn out to be the same as the product of 400 and 750. And that product is the speed of light, because the speed of light turns out to be equal to the wavelength times the frequency. But the frequencies are now quite astonishing. I mean, 750 trillion hertz, terahertz, 480 terahertz. And this is all just in a very small portion of what comes in from the sunlight, and a very small portion of the spectrum. I want to so these are pure frequencies. I mean, if you're here at 480 terahertz, it is really whatever it is that is fluctuating, and it's the electric and magnetic field that's coming through space, is fluctuating at 480 trillion times a second as it goes past your eye. And if you combine that through two slits or through a diffraction grating, you will get a geometric pattern that is will tell you this. Now, there's one other thing that I'm adding here, because I am going to make a little digression in a minute, and that is that there is an energy associated with each of these wavelengths, with each of these frequencies. And the energy goes up with frequency. And I'm using my favorite unit of energy, which is the electron volt, which is not exactly the household unit, but it's very much the household unit in physics. And you don't really have to know what an electron volt is. It's an extremely small amount of energy is what it is. But it turns out that it's a characteristic energy of chemical interactions. A few electron volts is what energy is involved, usually when a molecule is hitching, well, actually when a couple of atoms are hitching together. And it is also this energy, about 2 electron volts, is visible. Yeah, question.
Was that 2 electron volts per wavelength?
It is. You're pushing me ahead a little bit, Larry. But of course, what happens, what we're going to find is that although we've been talking about all this nice wave properties, it turns out that light has a very particle nature. That light comes in chunks, and the chunks have an energy which is related to their frequency. And so a 480 terahertz beam of light will be composed of photons, which is the name we give to the chunk of light. And each of those chunks will have an energy of about 2 electron volts. And then as you step up the frequency, it still stays chunky, but the energy of the chunks goes up. Now, people don't like the word chunk. That's got a lack of dignity. And so they call them quanta. And because that's what the word quantum means, it means chunk. When you go in and get an X-ray from your doctor, you'll be up not at the EV, you'll be up at the thousands of EV. You'll be using wavelengths so short that the energy is very high. That's one of the reasons people are very cautious handling radiation from X-ray machines. And they don't put a lead apron on you, but you'll see that whoever your technician is wearing a lead apron when they, well, they will put lead over you if they're not X-raying that part. Anyway, we'll come back to this issue of energy and wavelength and frequency. So wavelengths get shorter as the energy gets higher. Frequency gets bigger as the energy gets bigger. And that's an important idea. I'm going to try an experiment here. So once again, bear with me, because I want to show you this business about constructive interference. I want to show you some more about superposition and how interference arises from just adding together waves. Let's see. So here I go back. Yeah, that should work all right. All right. I want to bring file. I want to do open recent. So I'm going to bring in something which, again, most of you know. And that is that you can add waves together. And so here I have a live time. It's much slower when I'm doing it through Zoom, I see. All right. Keep that in mind for the future. All right. So what I'm showing you here is something that you all know about, which is that you can add waves together very nicely. And what I'm doing here is I'm making a square wave by adding together sine waves. And I'm doing it more slowly than I like. I'm sorry about that. Okay, so what I've done here is I'm adding together a bunch of sine waves, which are multiples of their frequency. And this is summation sine. So I'm adding these things up. And those of you who have done signal processing know that a square wave can be broken down into sine waves and cosine waves. And that the more terms I put in the sum, so here, let's do this. This will probably cost me, again, more time than I want. I'll just add together 3 of them. And you see, it comes out bumpy. Suppose I only add 1. And there, now suppose I don't add any. So it happens that when I set the max to be 0, there I am with my cosine wave. Yeah, that's a cosine wave. Perfectly nice, smooth cosine wave. When I add a cosine wave with twice the frequency to it, it cancels some and adds to others. That's the superposition. That's the adding together. That's what's going on.
Charlie,
Yeah.
are you sure that isn't a sine wave? 'Cause it's going through
You're
zero.
absolutely right. It's going through 0.
Okay.
Quite right. Thank you. And I can make it, well, here, I can, well, not now. And so here it is. Here's my square wave. I can make the square wave up by the following trick. And you see what I did? I shifted the wave to the right. And I did that by adding a term in the argument of the sine function. And again, it's probably well known to most of you. What I've done is I've changed what we call the phase of the wave. And so this word phase comes up all the time in physics. We talk about 2 waves being in phase. We mean they'll cancel when they add. We talk them being, I'm sorry, when they're in phase, we talk about them adding constructively, interfering constructively. We talk about them adding destructively if they're out of phase. And the word phase really refers to the waveform's location relative to the origin axis. And what's important between waves is not the phase, but the phase difference. 2 waves that have different phase will probably undergo some cancellation. And if you have them 180 degrees out of phase, you get destructive interference. So that's my story on that. But I want to show you one other thing, because if I'm telling you that, I mean, sort of the point of today's talk is that we're going to have a sort of disjunction between waves and particles. But I want, while I'm here, I want to show you that you can, with waves and superposition, begin to build something kind of particle-like. And in fact, you can sort of see something like that happening here, because you might think of this as a place where there isn't anything, this stretch in here. And then all of a sudden you have a place where there is something, and then there isn't. Now, if you were to compress this and make this narrower and narrower, it would become more and more localized. It would be a pulse. I mean, again, I'm not telling you anything you don't know, but that pulse begins to look more like a particle than a wave. And so it is possible with by superposition, by adding together the right set of waves, it is possible to make something that looks like a particle. So here's my cosine wave. Got it? Okay, Larry? Got it this time. This is a cosine wave going up and down very nicely. And then here's another cosine wave, a longer wave one. Here's the sum of the two waves. And you can see that works. Where the red one is going, the red one is being added to the blue one to get the green one. And so you can see here, the red is negative and it's combining to reduce some of the amplitude here. Over here, the red one is positive and the blue one is positive, and they both add, give you a maxima there. Nice constructive interference. Now, what happens if you start adding together a lot of these? Well, I added together in this general formula, I did exactly what I was doing down here with these three. And I produced this form here. But what if I add more than two waves? What if I add 20? Well, you see what happens is that I get a big bump here in the middle. In fact, I'm going to have to zoom out to see this thing. And you can see what's happening is that by adding 20 of these things together, I'm kind of losing what's in the intermediate space here, and I'm getting something quite sharp and large in the middle, not very much farther down the line. Here comes another one. So it kind of repeats. It's still periodic. But if I add, suppose instead of having 20 waves, I have 50. If I have 50, you see, this is getting sharper and it's getting taller. In fact, the area is staying pretty much the same. The area under the curve is staying pretty much the same. But the other guy, where is he? Well, he's out here somewhere. I better do it. There he is. He's out here at 325. So if I zoom out, there they are. So again, sharper, taller, farther apart. Those of you who know what Fourier analysis is know that I can stop doing summation and go to an integral. And what will happen is this guy will go off to infinity. This guy will get very, very tall, but very, very narrow, and begins to look like a particle. And I can make these guys move in my equations so that they move like particles. And they have energy and momentum like particles. So you can out of waves build particles. And in some sense, and the reason I'm telling you this is because in some sense, that's what quantum mechanics does. Quantum mechanics enables you to build your waves into particles, or it's more complicated than that, and I'll have more to say about it in a little while. All right, let's see if we can go back to PowerPoint without, okay, back here. So that was a little side trip to talk about how superposition can make waves actually look like particles. Now, this is another little digression. I want to show you, this is a little history, so think of it as a story. for the day. This is where the quantum comes from historically. And this is the reason Planck's constant is called Planck's constant. And this is the beginning of the end of classical physics. This is Max Planck, 1858, so 19th century, educated in good Prussian schools, a kind of responsible physics citizen, but a man of a very strong intellect and a believer in thermodynamics and statistical mechanics, a field of physics which often becomes rather abstract, but has enormous deductive power. I'll give you an example. Once people knew there was such a thing as radiation, electromagnetic radiation, you could use thermodynamics to predict properties of that radiation coming from a heated body. You didn't have to know anything about the body. You didn't have to know much about the radiation. You had to know it was radiation. But quantum thermodynamics would tell you things. It would tell you that in a certain ideal kind of body, a body where all radiation is absorbed and then equally rapidly re-emitted, that body will always have a total amount of radiation proportional to the fourth power of the temperature. People knew that without really knowing much about radiation or hot bodies. What was interesting was it turned out you could check it experimentally. And you got into a problem, which I'll explain in a minute. But Max Planck found a solution to the problem, and thereby invented the quantum. He really invented the photon, although he didn't know it. And we had to wait for Einstein to tell us that Max Planck had invented the photon. So maybe Einstein invented it then. Anyway, here's a little history, as I say. So here's Planck. This is a very busy slide, but here's Planck and his constant H. And the story has to do with black body radiation. And black body radiation is an idea. It comes out of early recognition that if you're going to have two bodies in thermal equilibrium, then it will be that if one is radiating a range of frequencies, maybe different intensities of each of the different frequencies, the same body will absorb those same frequencies with the same intensities that they're being absorbed. That's a little bit of a qualitative thing. That's kind of the black body radiation idea. What you would really like to have, though, is a real black body, because it turns out real bodies, some will emit some frequencies with, they'll absorb and consume some of the frequency, and it's complicated. But an ideal black body, I'm waffling, but an ideal black body will absorb everything that hits it, and then it will, at a certain temperature, re-emit all that same stuff. So where do you get such a black body? The 19th century physicists were very clever. Someone says, oh, have a box with a hole in it. Then you shine radiation in the hole. The radiation goes in the hole, it bounces all around in the box. Eventually, emitted and re-emitted from the walls, it comes back out the hole. That hole is your perfect black body. You can actually do experiments on that. You can measure what was of interest called the spectral density. And spectral density just means how much energy comes out at each different frequency. Here's a graph over here. This is a graph, and it is a graph of spectral density versus frequency. And for different temperatures, but just look at the yellow curve for now. And you can see there's a lot of energy coming out at somewhere around 700, maybe 600 terahertz. Well, if you think back to the spectrum that I showed you a while ago, 600 terahertz is right in the visible. So this is a hot body, and it's glowing. And in fact, if we go down here to 5,000 Kelvin, that's the absolute temperature, the red curve, and we look here, we see he's got his frequency coming out right around 400 terahertz. And 400 terahertz is, again, getting down towards the, well, it's in the yellow, red, green, actually. So, but that's by the way. I want to tell you the story of what Planck did, and I hope I can convey this because it's a lovely story, I think. So, first of all, thermodynamics, classical thermodynamics says it's got to be that the radiations that go on and back and forth inside the box, in with the walls of the box, in the end, when it's in equilibrium, cannot depend on what those walls are made of. You just poured radiation in there and you let it bounce around, bounce around, bounce around. And after a while, some of it leaks back out the hole, and it comes out of the hole with this distribution of energy versus frequency. But it's going to come out, it isn't going to make any difference what you make the box out of. It's going to come out with this. And so Planck said to himself, well, he said, if it doesn't make any difference what the box is made of, why don't I pretend the box is made of harmonic oscillators? You know, little tiny charges, maybe dipoles that would go back and forth, wiggle, wiggle, wiggle. Because, he says, physicists can do a fairly well calculate the properties of emission and absorption of a harmonic oscillator. Paired charges. We can do that. That is, you learn to do that very early in your career. And he said, so Planck said, look, if it does not make any difference what the walls are made of, then I can do all the calculations with this thing, and I know how to calculate really well, and I will get a theoretical expression for what the experimentalists are measuring. And this is an idea that had been around for a while, but so he sets out to do that. He's going to calculate this little symbol here, use of nu. That is the spectral density. That's the name of this curve here. And it turns out that it is equal to a couple of things you know well: 8. Everybody's up on 8, and pi. Pretty good on pi. The speed of light cubed down here. That's a little weird, but okay. And the frequency that you're talking about squared, and the average energy of this collection of oscillators. So his problem is really, he's got to calculate, or physicists' problem is, they have to calculate the average energy of a bunch of oscillators, something you can do. And in fact, I can remember from sophomore thermodynamics, which I took as a graduate student, you get fairly easily, the average energy of a bunch of oscillators is going to be Boltzmann's constant times the temperature. Well, if that's true, then I can tell you what the spectral density is. I just put KT in where I've got the E bar. And what do I get? I get a disaster. Why is it a disaster? Well, because it says that the energy density doesn't go this way. It goes, doesn't turn over. It just goes on getting higher and higher and higher. In the business, when it happened in the end of the 19th century, they called it the ultraviolet catastrophe. And what they meant was, Jesus, it sure didn't work out very well, did it? Your theory, it goes up as nu squared. And now here's where Planck does something which nobody had thought of until then. He does this right around 1900. He says, look, if if the energy of the oscillators doesn't vary smoothly and continuously, so that when you calculate the average, you're going to get KT, what if the energy of the oscillators is always an integer multiple of something, some little fixed amount? So all of a sudden, you're not, as we would be thinking of it, doing integrals and sort of adding and adding and adding and adding smoothly. You're adding up sort of bars in your graph, or anyway, you're adding them up. So you're getting integer multiples of a chunk of energy. And he said, and again, once he said this, classical thermodynamics said, oh, well, your chunk, this is what your chunk has to be. And I put it down here twice. Put it down here in black because it's the result. I put it down here in red because it's such an important result. And I put it down here twice because it is the beginning of quantum mechanics. It is pushing on us the problem of the stuff that we thought was continuous electromagnetic radiation. Somehow or other, it's chunky. And if you do let it be chunky, you can calculate what the average energy of a group of oscillators are when the oscillators can only absorb and emit in chunks. And you will get this expression here, and you'll go back and you put it in here for E bar, and you'll end up with this expression here. And this baby matches the experiment, or we should maybe say the experiments. This is a perfect description of the experiments that people are measuring stuff out of. I mean, it is a triumph of a sort. It is a triumph, but it is also screwball, and it is just enormously disturbing. It was disturbing to Planck. He wasn't really sure he believed it. It certainly worked. It wasn't as ad hoc as I make it sound. He knew some stuff about these curves. He knew some stuff about the experimental data that made this entirely reasonable. But if I were to go to Grapher and just put this in and plot versus frequency, you'd see all these curves come out perfectly. I mean, he had it. He was right on the money. But, and he, what is it? You know, he put the cat in with the chickens. This was immensely disturbing to people because it worked so well, and it just was so contrary to everything anybody was thinking about radiation there. So that's my digression to talk about Planck. What happens next? Well, what happens next is it's quite interesting. Again, here's a little piece of stuff that had been around since the 1880s. Well, I'm going to tell you what happens next. What happens next is Einstein picks up this idea of the chunk of the quantum. And he says, well, again, for quite very fundamental reasons, he says, you know, it isn't that these oscillators absorb in chunks and emit in chunks. It is that the stuff itself is chunky, that the electromagnetic radiation is made of quanta. Now that's a much more radical idea than what Planck was willing to admit, although Planck certainly knew his idea was radical, and he was basically saying, you know, certainly looks right, and it means there's just a lot of other big changes coming in physics. And here they come. So 1905, only 5 years after Planck, we have here our patent examiner, Albert Einstein. And I'm going to go back to the previous slide. So here we are, the photoelectric effect. Now, this was, you might almost think it was a kind of minor effect, but it was known since the 1880s. It had been seen in the laboratory. Incidentally, it was seen at the same time that the wave nature of electromagnetic radiation was being established to absolutely everybody's satisfaction by Heinrich Hertz. There was showing up a kind of strange effect that we will now see is entirely consistent with light being in quanta. This was called a photoelectric effect. Heinrich Hertz, famous German physicist, was the first person to use Maxwell's equations. Well, Maxwell's equations theory said, you know, there ought to be electric and magnetic fields that sort of hand over hand propagate each other through space. There ought to be something in space. And hey, he said, isn't it strange? My theory says they will propagate with the speed of light. What a coincidence. Well, of course, there's no coincidence at all. It's the fact, and that's what everybody was realizing. Oh my God, do you think electromagnetic radiation is really and light are the same thing? So this is what's going on in the 1880s. Excuse me. Heinrich Hertz makes a laboratory experiment in which he generates the first electromagnetic radiation in the laboratory and sends it across the laboratory to a receiver. It's the first radio transmission, really, except that what he's doing is he's sending electromagnetic radiation over to a pair of electrodes that are set up with capacitance so that they are in a resonant, electromagnetically resonant to the incoming radiation, and that radiation causes a spark to flow, spark to jump between the electrodes. That's his detector. So he sends radiation, he thinks he's sending at a certain frequency, he sees a spark. So he must have sent radiation. He's discovered the radiation in the laboratory. It's a wonderful moment. But he also observes that if he puts different kinds of filters, if he puts glass in the way, he has to put the sparking electrodes closer together to get a spark. And whereas if he's just letting the radiation go through the room, the electrodes can be a little bit farther apart and still get a spark. And so what he is discovering is that if you have a metal and you're shining radiation on it, and the radiation is ultraviolet, the blueness of the spark was ultraviolet, it will cause electrons to jump out of the metal. This is known as the photoelectric effect, that you can make electrons jump out of a metal by shining ultraviolet light on it. There are other ways. And the electrons come off with different energies, some not much, some more. And the energy, there turns out to be a maximum energy that you can have. So the energy, if you turn the frequency of the light down that you're shining on the metal, eventually get to a point where no electrons come off, they stop. You turn it up, nothing happens, turn it up, nothing happens. You turn it up over a certain amount of frequency, bang, they start to come out. They come out with, some come out with not much energy, some come out with little energy, but some come out with a surprising amount of energy. I mean, you just went from nobody's coming out to suddenly somebody's coming out, and they're coming out with a maximum amount of energy. And it turns out no matter how much you turn up the intensity of the light, you do not get them to come out with more energy. You may get more of them to come out, but they don't come out any faster. If you turn up the frequency, they'll start coming out faster. So what's going on? And Einstein is the one who says, here's what's going on. He's saying, you have energy coming in photons with an amount of energy which is Planck's constant times the frequency. And that amount of energy is all the energy that's being delivered to the metal. If that isn't enough energy, that is, if the frequency is too low, no photon is going to make any electron come out. Once the frequency is high enough and this energy is big enough, it's going to knock an electron out. Some of the energy of the photon will go to breaking the electron loose from the metal. The rest of it will go to accelerating the electron. it was a very bold idea, 1905. So it's only 5 years after Planck. Einstein is saying the radiation delivers its energy in chunks, in quanta. This is the beginning of quantum mechanics, the quantization of radiation, the quantization of the delivery of energy, the quantization of the absorption of energy. And here he says it. This is, I'm quoting Einstein, according to the assumption considered here, in the propagation of a light ray emitted from a point source, the energy is not distributed continuously over ever increasing volumes of space, but consists of a finite number of energy quanta localized at points of space that move without dividing and can be absorbed or generated only as complete units. Well, that's what Planck said. He said the part about generated and absorbed as complete units. But Einstein is saying the stuff itself is made up of complete units. So we have here now, we have wave-like properties of light interference, and we have particle-like properties of the photoelectric effect. Life is hard. Nobody believed him, least of all Robert Milliken, who was working at that time at the university. Well, you know, I can't remember whether he had moved from Chicago to Caltech yet when he did his work. I think he had moved to Caltech. Anyway, he did the following experiment. Let's see, I wonder, is this diagram? Yeah, I guess you can, the diagram is, this is very clever. So the idea is that you want to shine light of a known frequency on a metal and see what the energy of the electrons might be that come off. The trouble is metals have oxides on them. You know, you have metal, you can scrape away the oxide and almost immediately you got an oxide again. And the light, the quanta of the light, the photons, will interact with the oxide differently than it will interact with the metal. So you don't really know what you've got. So what he did was he had a apparatus. So he had an apparatus built in a vacuum chamber. All right. So here, this is a big glass bulb. And here he has a drive motor. And here he has, on the end of the drive motor, he has blocks of alkali metal, because alkali metal will give off electrons for the lowest frequencies of light. Cesium is great. Sodium is fine. They really don't mind. I mean, they will be responsive to visible light, maybe in the blue. But the surfaces will oxidize very quickly. Well, you can put it in a vacuum. Nobody could make a vacuum that good in those days, and still really they can. I mean, put a piece of sodium in what we call a vacuum, and fairly shortly, the sodium surface will have oxide on it or crap on it from deposited out from your vacuum. It's a good way to clean up your vacuum. But what he did is very clever. So he has a drive motor here, and down here he has a little knife, cutting knife. And so he drives the ring around till the little block is in front of the knife. He spins the knife around. It grinds the surface off the block. He rotates the block back fairly quickly. Where'd my arrow go? He rotates the block back quickly, shines light in while he's still got a clean surface. And he does the experiment for a while. And absolutely contrary to what he expected, he validates Einstein's theory that this energy is coming in chunks. We got quantums. Well, and so here's an even better picture. I didn't realize I had this one here. All right, so you can see a little better. He has a cutting knife here. He cleans the surface off with a cutting knife, rotates it around, shines the light in, and then he says, well, the electrons are going to come off with a maximum energy. What's the most energy they can come off with? The most energy they can come off with is the energy of the photon that went in minus the energy that it takes to break the electron off the metal. And that's a fixed number. So he says, all right, let me try this as a function of frequency. And so here he is, he's measuring the maximum energy along this axis. He's measuring the frequency of the light along this axis. And just look at that line. That is so beautiful. He's got the frequency, kind of low frequency, comes off with a certain maximum energy comes off here, higher frequency up here, higher frequency up there. This is a straight line, which is the equation, is the straight line of this equation. E max along the y-axis against frequency. Oh, but what's the slope of the line? Any takers?
Planck's constant.
It's Planck's constant. You got it. But I suspect that Dick Wagner knew the answer. Anyway, and that's right. So here we have not only verification, validation of Einstein's idea, we also have a nice measurement of Planck's constant. Milliken, just a byword of Milliken. Go back a moment. When I was in graduate school, we were studying Milliken's experiments, and Milliken, and he measured the charge. He was the first to measure the charge on the oil, measure the charge of the electron, and really measuring the quantization of charge. And he was no small self-promoter. He spent a certain amount of time in Europe, frequently campaigning for his Nobel Prize, which he well deserved, but he did get it when he did get it. But I remember that I think it was my professor said that in the profession, it had become known that there was a unit of self-conceit, and that the unit of self-conceit was the can, but that was too big of a unit. And so you had to use the Millikan, and we did, so you go to graduate school, and what do you remember from graduate school? That's what I remember from graduate school. All right, so we've come now to the other side of the problem. So here we have this stuff, these electromagnetic radiation, and it turns out to be chunky, turns out to be particulate in some way, and yet it does do interference. So it is a wave. And so you're walking around with these two really contradictory concepts banging together in your head. And they still bang together in a head. But here, to make it much worse, comes the other side of the story, because we had stuff that we knew was particles. I already mentioned Milliken measuring the electric charge on an electron, and we knew the mass of an electron by this time. We know it's 9.11 times 10 to the minus 31 kilograms. It's very small, but it has a very distinct mass, and you can detect a single electron. You can do all the things you think you ought to be able to do with a particle. And so here comes Prince Louis Victor Pierre Raymond de Broglie. Now, I like what we've got here, and I think we should realize that here we've had the verification of the quantum nature of light by a patent clerk. After all, that's what Einstein was when he wrote those papers. He was working in the patent office in Bern. So, I have two kids who work for the patent office, but not much so far in the way of advances in physics, but okay, I'm waiting. I've got lots of time. But so you have a patent clerk sort of breaking down one conception of the wave nature of light. Now we have a prince breaking down the particle conception of matter. And that's de Broglie. Now he gets to be a prince because he is in the house of de Broglie, and it turns out that all the let's see, what is the firstborn de Broglie boy is a duke, and all the other boys are princes. So it's not as though he's going to be king. But if his brother dies, he will get to be duke. In fact, his brother did die, and so before 1987, Prince Louis Victor Pierre Raymond de Broglie became Duke de Broglie. Well, he was looking at Einstein's theory of relativity. And he's looking at the theory of relativity, and he was saying, there's a kind of symmetry in here that's very attractive. And he says, the symmetry is that it leads me to think that if you took Planck's constant and divided it by the momentum of the particle, those particles would behave as though they had a wavelength of lambda equal to Planck's constant over the momentum. Now, I'm not going to show you why this is a reasonable thing to infer out of relativity, but it is. On the other hand, it's pretty bizarre. How did we get to wavelengths? And isn't that silly? I mean, has anybody seen wave-like properties of electrons? Well, maybe not quite yet, but it was only a matter of a short time. Today, we can do the following experiment, which I think is very beautiful. And so let me show it to you. All right. So I'm going to show you this black screen here. And I'm going to turn it on. And this is actual experimental data. This is a recording. Some of it's speeded up, some of it's slowed down. If you read the fine print, you'll see. But what's happening is electrons are coming through an apparatus, which is essentially a double slit apparatus for electrons. And the electrons are being detected. And so I'm going to turn it on, and you watch. What you're going to watch for is little tiny dots of light on this black screen. So it's going to be hard to see at first. Come on. Go. All right, here we go. Well, there's kind of one. There's one. See it? There's another. So these electrons are being detected. Here comes more. There's another. There's another. There's another. There's another. And now they're going to speed it up. So maybe we'll get a bunch of them. See, they're coming in faster now. So they sped up the time lapse. But what do you see happening? Do you see it yet? Do you see it? You see fringes, band of intensity, band of not intensity, band of intensity, band of not intensity. Those electrons are producing a double slit interference pattern. Now, if you're a reasonable person, this should just creep you out. How does an electron do that? One at a time. See, before we had our waves and we could kind of see what was going on because you had a piece of the wave overlapping with another piece of the wave. That's not what's happening here. We have an electron going through an apparatus, and somehow that apparatus has told the electron, don't go here. It's okay to go over here, but don't go here either. And it's okay to go here. This is very clever electron, or very obedient, or obedient to what? You see, that's where a lot of the mystery comes from. But it certainly says, oh yeah, these things that we thought all the time were particles, they're exhibiting interference. So there has to be something wave-like about it. All right. And here just a sequence. These data were taken by Akira Tonomura, who was working, oh geez. Anyways, he was a lifelong employee of one of the major Japanese electronics companies, and I should remember the name, but it slips me at the moment. And so here's just a succession of pictures, photographs, very nice fringe by the time you've waited long enough. And here is Akira Tonomura, who did his interference one electron at a time.
So what can be interfering if there's only one electron?
Isn't that an interesting question, Jerry?
Interference implies that there's two things.
Well, maybe not anymore.
Right.
But I mean, you've just asked the question which everybody was asking, what's going on? And in fact, just here another minute or two, I'll probably have to go through it rather briskly. I'll show you that photons can do the same thing. Photons interfere one photon at a time. And so you have exactly the same problem, or you have exactly the same properties in both the things you think of as particles. But nice man who did these beautiful pictures, and I thought he deserves some credit because he doesn't get it. Here's his apparatus, just to show you when somebody says, "Oh, I did a double slit experiment with electrons." You have to fill a room with something. You have to have a source here that the electrons are going to come off the source. You have to have some rings which are at voltages of 3 kilovolts and 50 kilovolts, and they're going to focus this and clean up the beam of electrons, so you're dealing with monoenergetic electrons, and then you're going to focus them, and then you're going to run them in here. This is your double slit. It's an electrode with a positive charge on it and electrodes with negative charges on it. 10 volts. Not much voltage difference between this and these plates, but the electron beam coming in here is attracted towards, it's got a lot of energy, and the effect is to be swung. Some of the beam will go this way, or put it another way, sometimes an electron, you say, will go this way, and sometimes an electron will go that way. And the net effect is that when you combine the two electron paths down here, where so that whether the electron went this way or that way, it ends up going the straight way through here into this micro channel plate where it's finally detected, position sensitive detector. That's what you were seeing, the little dots of light show up on back here. 2,000 times magnification. Anyway, there's a lot of stuff going on to get here. It's very beautiful. Now, little digression, but I thought, again, worth mentioning to you, important implications of lambda equals h over p, wavelength. It says that if the momentum is big, the wavelength is small. You put a big number in the denominator. Well, that tells you, if you suppose you want to be, you want to study something small, really, really small. Maybe you want to study an atomic nucleus. Maybe you just want to study an atom. Maybe you just want to study the lines in the grating. They're pretty small. Well, if I'm going to do an optical grating spacing, I'm going to need a probe which is about 10 to the minus 6 meters, a micron. Something quite short wavelength, but it's not optical. It's getting there though, and it has a momentum that corresponds to an energy of 1.24 eV, almost optical. But what if I want to study an atom? Well, an atom is this size. If I put an atom this size in there, I get 12.4 keV. I'm going to need an X-ray machine making 12.4 keV X-rays. Well, suppose I want to study the nucleus in detail. I want to get right down inside. I want to see the protons. I want to see the neutrons. So that's 10 to the minus 14 meters. I've got to have a probe of 124 million electron volts. I need a fairly hefty accelerator. Well, it isn't actually. What if I want to actually study the proton? I want to begin to get, is there structure in the proton? Is the proton really just a round little positively charged ball? 10 to the minus 15 meters. You can study the proton, but you're going to need an accelerator of 1.24 GeV. See how it goes? You want to study the insides of a proton? I mean, you want to get inside. Look at the sort of at the structure, thousandth of the diameter of a proton. You need a teravolt. You need a big machine at Fermilab or a big machine at CERN. You want to study the smallest length that we think can exist in nature? Well, you can't. It takes too much. But that's what you'll need. But here, just sizes and wanting to know about things of smaller and smaller sizes tells you you've got to build probes with it, which have wavelengths that correspond to these energies. Just kind of interesting to see how it's right there in that basic structure. I went the wrong way, sorry, back. All right. Want to talk a little bit about photons and photon interference. And here is a device, much loved in the business, a photon interferometer. It's called Mach-Zehnder interferometer. And the idea is very simple. I'm going to have a source here. And I'm going to have photons come in here. And I'm going to have a beam splitter. Beam splitter is a perfectly simple device. It consists maybe of a glass block with a partially silvered interface. Partially silvered means it'll reflect some, but it'll transmit some. So the photons are going to come in. If you imagine a bunch of photons, if you imagine a wave coming in, some will go this way and bounce off the mirror and come over here, another beam splitter, and be sent into some here and some sent to here. Some of the photons will go through and they'll come over to this mirror and they'll go up here, and some will go through and some will go there. The result is that at C and B, you'll have, if we think of this as electromagnetic waves, you'll have the two waves coming, having traveled maybe different path lengths, maybe a little bit different. If the lengths are exactly the same, then the crests will both arrive here at the same instant, and you'll have constructive interference. If you move this mirror a little bit so that this path length now is a little bit different from this path length, then the crests of this wave will arrive a little out of phase, a little out of sync with the crests from this wave, and you will have partial interference. And if you move this so that the valleys of the wave arrive exactly in sync with the crests of this wave, you'll have destructive interference. So nice, simple idea. Now, here's what you can actually do. Here's an experiment, quite lovely. I can have a source which produces two photons at once. Nice. And they go in opposite directions. So here comes a photon this way, or a wave, or whatever you want to think of it, but I'm thinking of it as photons. It is photons. So, and one goes this way. We usually call the one that's going off into the apparatus, we call that the signal photon, and the one that's going off here is called the idler photon. And then what it enables us to do is to know when a photon has entered the apparatus, because there'll be a click over here or something. Well, it detected something, and yet something will have gone this way into the apparatus. Well, So now I know there's only one photon in the apparatus. And now we're back to what was bothering Jerry before, because if I have the mirror set here just right, so that this path length and this path length are the same, then I will get coincidences up here at signal B1, B2. And if I start moving this mirror a little bit, I'll lose the coincidences. But this is one photon at a time.
If it's quantized, how does the photon interfere with itself? It can either go up or it can go sideways. It can't go
Exactly.
both.
All right, so now you've come to right where I want to be at part one of quantum mechanics. Quantum mechanics is forcing you to say, somehow or other, that photon goes through both slits at once. That photon has to know about both paths. Now you say, well, what if I check and see which way it went? You know, I could actually tell you which path the photon went. I mean, I can set up an apparatus to do that. You know what happens? As soon as you can tell through which slit the photon went, the interference pattern is gone. You will not get an interference pattern. And you can spend an enormous amount of ingenuity trying to figure out ways to know that that photon went through one path or the other path. And when you get done, you will not have an interference pattern. So this is the beginning of where you have to make your peace with quantum mechanics. Somehow or other, a photon can go through, a single electron can go through two slits at once. And indeed, in the mathematics, you can find yourself saying that. I mean, you may say you don't like to say it because you don't want people to lock you up, okay? But you can end up saying that and the mathematics won't disagree. It's okay to, you can actually reason that way and come out with an answer that's correct. I come to really to the sort of pièce de résistance, which is here. And I'm not sure that we have time enough in life to understand what's going on here. But this is a beautiful experiment done by a couple of guys at University of Rochester. And what they have is a setup in which they're producing photon pairs. These boxes marked N and NL. He's got a big laser out here, and the big laser pumps something into each of these nonlinear crystals, is what they are. And the nonlinear crystal has the property that it will convert one of the argon photons into two photons. And so out of here, out of the box will come an S2 photon. Out of box 2 comes S2, a signal photon, and I2, an idler photon. So you can, so if you are down here with your detector and you detect your I2 photon, you know the S2 photon has gone this way. The S2 photon goes up here to this beam splitter. The NL, the nonlinear, produces an S1 photon and an I1 photon. And the S1 photon goes up this mirror, hits this mirror, and comes down. So these two photons arrive at DS. And one photon could have come S2 this way to get here, or another photon S1 could have come this way to get here. Well, if you can tell which way they came, well, let me put it the other way. If you can't tell which way they came, if it's, and I'll show you in a second what's going on, you will find that moving this mirror up and down produces an interference pattern. You will have maxima corresponding to the case where the two paths were exactly the same, and you will have minima corresponding to the place where you've moved this mirror enough so that one path is 1/2 wavelength longer or shorter than the other. You'll get that nice interference pattern. But what about these idler photons? This is really cool. See, I've got a photon coming off here, and I've got a photon coming off there. Now, here's what's beautiful. If I have everything so perfectly aligned that the I1 photon and the I2 photon come around here to this detector, and I cannot tell whether the photon arriving here is an I2 photon or an I1 photon, then I can't tell the paths apart, and I get the interference pattern. But if I put a filter in here, not in here, not anywhere up there, but I put a filter in there so that I block the I1 and only the I2 comes down here. So I always will know that if I get a click here, then the photon that's come up here went this 2-path. I do not get an interference pattern. So putting a filter in here makes the interference pattern go away between these two photons that have nothing apparent to do with this filter. You can even do this. You can go back and get everything so perfectly aligned and take the filter out that the I1 and the I2, you can no longer tell when you get a click here, whether it's telling you there was an S2 or an S1. But now suppose you change the alignment just a little bit. Well, if you change the alignment a little bit, then you can, in principle, you could begin to tell whether you had an I2 photon or an I1 photon. It would depend on where on this detector it struck. Now, you don't even have to do that. It just has to be possible to do it. And as soon as it is possible to do it, the interference pattern returns. As soon as you can no longer tell which path the pair of photons that you're producing traverses, the interference pattern comes back. Anything you do that will distinguish the two paths, and that interference pattern is gone. It is only wave-like when you can't show that it's particle-like. And similarly, I suppose, it's only particle-like. Well, that's a good place to stop part one, I think. I'll tell you what I was thinking of doing for part two is that, I mean, we may want to talk about this, some more, because it is creepy. But the other great discovery of quantum mechanics, or the other great property of quantum mechanics, is that systems have very distinct energy states. You can imagine an atom as a ball of charged particles, okay? Something scrunched together in some geometry. Not all geometries are possible. You can't imagine rotating your electrons and your protons around continuously. They are in like ratchet mode. You're in a certain energy. You want to change things. You can change things, but you can only change them chunk to a different energy state, chunk to another energy state. So that discreteness of energy states is very quantum mechanical. It's what makes us possible. It's what makes chemistry. It's what makes biochemistry work. When you think, we've been hearing all these nice talks about CRISPR and how all this stuff, how all these little machines work, and how the molecules come over and they lock on, and the RNAs come over and they do all this and that stuff. They could not do that if quantum mechanics were not the valid theory of chemistry, because they would just be all kind of mush. The fact that they have structure and that they can match and fit pieces together like Legos has to do with the fact that that's their ultimate quantum mechanic nature. So for part two, what I wanted to do is talk a little bit about that. Although coming to the end here with the Mandel-Ho experiment is a way to leave everybody kind of miserable in their miserably discomfortable. Well, and Jerry has evinced so nicely. Thank you, Jerry. All right. So I don't know. I got some questions.
Charlie?
Yeah.
So what you and Jerry may be saying is there might be some as yet undiscovered phenomenon going on.
Well, everybody, that's a good, maybe that's part 3, Bob. I'm not averse to that in principle, but I sure as hell can't see where it is. Of course, that would be the truth of any really profound change. I mean, I wouldn't be immensely surprised if it turned out our understanding of space-time is deeply flawed in some way. But the search for kind of counter theories to quantum mechanics, the search for hidden variables, sort of little machines that are going on. A beautiful example of quantum mechanics at work is radioactive decay. You have a uranium nucleus. No, let's go with the tritium nucleus because we don't have to wait so long. And within 13 years, half of them will be gone. But you look at a tritium atom, you have no way of telling when it's going. You do not know. And there is no way, we believe, there is no way in principle to know when that one will go. That's very creepy to Newtonian thinking. You know, there surely somewhere deep inside the tritium nucleus, there's an alarm clock, and somebody has set it, the alarm clock, and when the alarm clock goes off, that guy is going to decay. Well, I mean, you can do experiments to look for the alarm clock. There's no alarm clock. It's not going to happen. It is really random, and that randomness is very bothersome. It means, you know, I like to twit my physics. You know, we have our household gods, and Newton is certainly one of them, and justifiably so. But he was deeply wrong. He was wrong in 2 ways. I mean, he was wrong about gravity at a very profound level, and he was wrong about sort of the deeper nature of matter, and maybe he was right about particles of light, but not quite. It won't get there.
Charlie, could you explain how you can take one photon, and if it's quantized, how do you send it down 2 pathways if it's quantized?
Well, that is the question. The point is, you have experimentally, you have no information about its degree of localization, its degree of spatial localization. You have no idea where it is in space, and so it can know about the 2 paths.
So it's quantized, but not really. It's
well,
not
it's
really
going to
a
arrive
chunk.
when you go to collect it. You know,
It
at the
becomes
end,
quantized again.
I mean, there's a chunk of it, and maybe the chunk is spread out. You know, you're picturing interference as an interaction with the slits, and that it's not. You know, it is not bouncing off the edges of slits, and you can the physical. What you need to make it physically distinct is 2 separate paths, and there are lots of ways to do that besides the 2 slits. But it is. Go ahead, Dick.
Quite possibly what you had to do is explain Schrodinger's box experiment to answer Jerry's question.
Yeah, I think I'll leave it at that though right now, and save that for part 2. I do think that it's nice to see that you know, Einstein didn't like the ultimate randomness that underlies quantum mechanics. He did not like exactly what you've disliked, Jerry, which is in the end, there is some kind of loss of localization of what people call local reality that we take for granted. And when you get down at the quantum level, it's not there.
And the cat got out of the box.
Schrodinger posed the cat paradox as an example of how absurd the theory is. He wasn't trying to get people to kill cats or even do experiments with heavy molecules, big molecules. He was just saying, isn't this ridiculous? And there's a couple, you know, it's kind of like didn't Wheeler coin the term black hole because he thought the idea was so silly? But that's what happens with our silly ideas. We get used to them.
Charlie, you probably know about Dave Pritchard's experiment with single atom interference. It was essentially the Mandela experience, but
Yes.
with an atom. And as you learn a little bit about the path, the interference patterns decreases a little bit. So you can continuously go from not knowing about the path to fully knowing about the path for atoms.
I mean, that's beautiful, Dan. I thank you for bringing that up. Yeah, I mean, I know about it, but it's I haven't worked it over the way I have worked some of these other things over. But anyway, that is a beautiful experiment. And Dan makes a point which I think is interesting. Is we have lasers which are atoms interacting. No, we have lasers which are photons produced by interaction of electrons with matter, but you can do it the other way around. You can have lasers of particle waves interacting with standing wave lattices of electromagnetic radiation. And I mean, we're just stuck with it, you know, and Bob was asking if there's something down there. I don't think there's anything down there. If there's going to be something change, it's going to be something much more profound somewhere that.
No, I wasn't referring to any physical thing.
No, well, okay. I was taking it as implicit.
I was thinking maybe some unknown property.
Yeah, well, I think, yeah.
I keep thinking that perhaps part of Jerry's question may be answered when we consider what you showed us earlier about each particle being the superposition of a very large number of waves, and the more waves we have, the greater that number, the sharper it becomes. Now, when we consider that particle, an electron, as a superposition of such waves, what would that superposition do as it goes through the double slit?
So I mean, that's a good point, Tony, but the real point, which I probably neglected, is, wave of what? What are we talking about here? And in quantum mechanics, that wave turns out to be a wave of probability amplitude, so that the square of the amplitude is location. And so, yeah, if I localize the particle in the apparatus, I'm making it very sharp, and it's only going to see one.
Yes, and I think
it's the other way around. But if I make, in order for it to see two slits, it has to be delocalized. I mean, the apparatus has to, it has to be delocalized enough so that it can, just as you have to, if you want your laser to be a double slit interference, you have to spread the beam of the laser so that it overlaps both slits. Yeah. But I haven't talked about waves of what's there's kind of interesting history. It has always seemed to me ironic. The physicists flocked to Schrodinger's equation, and right at the beginning, because it was a wave equation, and they knew about wave equations, and they knew a lot of stuff about waves and partial differential equations. There was a very slow, I think, migration to matrix mechanics in the Heisenberg formulation, because Heisenberg's formulation was linear algebra in matrix formulation that was unfamiliar to most physicists. It was unfamiliar to Heisenberg. When Heisenberg first formulated quantum mechanics as matrices, he didn't realize those were matrices. When he showed it to Max Born said, matrices. And in fact, Max Born always felt he should have gotten much more credit for the invention of quantum mechanics than Heisenberg, because it was also Max Born who said, the wave, it's a probability density wave is what you're talking about. So
are you leading us down, Charlie? Are you leading us down the pathway that there are no particles and they're just wave behavior that makes them look like particles?
I do not go there. I mean, how about both?
I don't know. Yeah,
There is, I mean, there are wavicles. I think we're.
there are popsicles too.
Yeah, but but you don't have to keep wavicles in your refrigerator. Okay.
One more little thing that I've always comforted at this point by, I believe it's a quote from Niels Bohr, that your theory is crazy, but it's not crazy enough to be true, which he stated, I think, at a conference on quantum mechanics in the 30s, or at least that's what it says all over the web.
And I mean, he's also famous for having said, if you're not disturbed by quantum mechanics, you don't understand it.